Thank you, Jianqiang, for the nice introduction. We have been knowing each other for quite a long time. And in the morning during the break, we had an interesting discussion about the hair color. So then he pointed out my hair color is really black. So I guess that's perhaps explains why Professor Hall and I do not have many direct sort of connections. But when I look back, I did find out that there's a lot of sort of indirect connections with Professor Hall through his students and also throughout his work. So a little bit, I just put on slides here because I work on simulation and simulation optimization. And those are the fields which are heavily influenced by Professor Hall and his students. And I also, during my junior faculty years, I worked a lot on perturbation analysis. So I actually look at how to apply perturbation analysis in the area of finance. So this is an area while Michael Fu, Jianqiang, and also Paul Glassman has worked quite a lot. And also during my junior faculty year, Michael and JQ also helped me a lot. So we wrote papers together. We also applied the grants together. And JQ and I become really close. I even spent my sabbatical year visiting him. And in the morning, he said that one thing he learned from Professor Hall is how to enjoy life. So during my sabbatical year, I learned from him. I still hope try to sort of catch up to his level. And also, I want to mention that during my junior faculty year, I mean, Shiren has been like a mentor to me. I actually attended his class. And one thing I can tell you that when I come out for tenure, he was the chair of the tenure and promotion committee. I'm sure that he has helped a lot. Did you? Okay, thank you. So this is what I'm going to talk about. I'm not going to talk about anything related to simulation and simulation optimization. Today I'm going to talk about something I've been working on in the past year. So something related to control. In particular, in this case, multi-arm bandit problem. So here's sort of the outline. But I look at this problem in a sort of a business environment, as now I'm in the business school. So I look at it from a sort of a more dynamic pricing angle. So let's look at the so-called online pricing problem. Suppose we have a company which sells a product online. So then customers arrive one at a time. So they're going to buy 1 unit of the product. If the price you give to this customer is lower than their willingness to pay. So assume that different customers coming in here may have a different willingness to pay, but however, we assume that every one of them, the distribution of their willingness to pay is the same. So then, so now what we have here is we assume that the company has a menu of different prices, let's say K prices, $3.99, $4.99, so on, so forth. Then the problem that the company is facing here is what price to offer. So when a customer coming in, what price to offer. So if you look at the problem, this is really sort of a classical learning and earning problem, or some people call it exploitation problem, which fall into the framework of the multi-arm bandit problem. So just to give a more sort of an introduction here. So the objective here, you're trying to maximize the cumulative profit by adaptively giving different customer different prices. So when they come, you offer them a price, they decide to buy or not. And so the decision here, so the decision maker here has two things. First, they want to learn. They want to learn what sort of willingness to pay distributions people have. Because with knowing that they can offer them higher price, they can have better profit. But on the other hand, to learn in information, sometimes that means some prices are not very attractive, but you want to learn. So if you learn that, there may be a potential loss. If you know the optimum price, you can give them an optimum price. That will always maximize your profit. But you don't know, so you have to learn. So through learning, you might have some regret. And the problem was in this online pricing or dynamic pricing context was first introduced by Rothschild in 1974 in the econ literature. And without any sort of assumptions on WTP distribution, the problem itself can be formulated as a multi-arm banded problem. For those of you who do not know multi-arm banded problem, I have one slide sort of give you an explanation what a multi-arm banded problem is. So multi-arm banded, so bandit meaning a thief, a robber who come into a casino. So there are many different slot machines there. So then the guy may decide to play the slot machine. So if the bandit knows which slot machine has the highest winning probability, so he's always going to pull that machine. But because he doesn't know, he has to learn. He has to learn. So that's the so-called multi-arm bandit problem. It was first formulated by Robbins in 1952. So it's really an important class of sequential optimization problems. And so the objective here is you want to design a sort of a sampling policy here. So which, you pull, the policy will tell you which arm to pull. So there are totally k arms here. So you want to maximize expected cumulative reward over a time period. Let's say from t from 1 to big T. So that's the cumulative reward is what you're trying to optimize. So if you look at, one way to look at the maximization problem of the cumulative reward is to look at regret. We're trying to minimize regret. If you look at the definition of the regret, it's quite easy. So suppose I'm the god. I know which arm is the best. If I call that R star here, so then my regret from pulling that arm would be mu I star. But because I'm not the god, I don't know. I have to use a policy to learn. So at a period t, so the arm I choose is this capital IT. So my corresponding profit is mu IT. So if the mu IT is equal to mu I star, that means I'm pulling the optimal arm. So my regret will be 0. Otherwise, I will have some regret. So what you try to do is to look at the regret and try to design a sampling policy which can help you to minimize that. So a few classical results in the literature. Land Robbins in 1985 has this very classical result. It basically says that no matter what sampling policy you're going to use, so the regret for the MAB problem has to grow at least in the order of log t. That means as the period becomes higher and higher, your regret here will also goes to infinity, and the lower bound, sort of the asymptotic rate, the minimum bound you can achieve is in the order of log t. Then in this literature, many sampling policies have been proposed trying to achieve that lower bound. So among different policies, one of the most famous policies is this upper confidence bound, UCB policy, which they are able to show that for any finite time t, you'll be able to show that the regret is bounded by a constant times log t. That's a very classical result. Because later on we're going to use this policy, this UCB policy. So I'm going to give you a little bit introduction here. So the policy is very simple. It basically says that for the first k place, you're going to pull each arm once. You pull each arm once, you get some information about that. For the subsequent periods, so what you do is for each arm, so you have already pulled them sometimes. So what you're going to do is you're going to calculate what is the average reward at the time. Then, so the average reward would be this mu j bar here. The j means it is arm j. But not only that, you're going to use the upper confidence bound. So here is only the mean, sample mean. So you're going to use the upper confidence bound. So you're going to add another half width of the confidence interval. And the half width here is defined as a square root 2 times log t divided by tj t minus 1. So the log t, so the t here is the current period, small t. And the capital Tj, t minus 1, is by the period t minus 1, how many times have you pulled arm j? Right? How many plays of arm j you have? That's a Tj. So this one. So they were able to show that with a very simple policy like that, you can achieve this lower bound. So the regret will increase to infinity in the order of log t. So you can apply this policy here directly to the online pricing problem, assuming that if you try to maximize revenue, so that means you only consider the demand times sales, or you try to say, well, the cost here is a constant, which does not change over time. But however, if you look at many of the practical applications, you can find cases where the costs actually change over time. And I just give you one example. When I went to US, when I bought my first car, I have to buy car insurance. Then I learned, before that I didn't know, so that your insurance cost and insurance premium is related to what the color of your car. I don't know if you know that. If you drive a red car, your insurance premium will be higher because according to the historical study, the data they collected, they noticed that people have red cars have higher chance of having accidents. But of course, I don't know. So you can think about a scenario like that. If somebody go online to buy an insurance product, the company will have some questionnaire for you to fill. You fill that. So once you feel that the company has some kind of assessment of your risk, based on that information, they're going to know something about what sort of cost you have. So therefore, with knowing this cost, so they're going to give you a different price. They're going to give you a different price. So now if we start to look at a problem like that, so it's very different from the MAB problem I talked about earlier, because in the original MAB problem, so what considered to be the best arm never changed. But here, what considered to be the best arm is actually changing with respect to your what particular cost you have. So we also have some other examples. If you think about the sales of some perishable goods, like gasoline, fresh fruit, so because the price, so the wholesale price change every day. So therefore, one let's say grocery store decide what price to sell that, the price also change every day. So that's another example. While varying cost is an interesting problem. So here's some notation here. So we have the capital T here, meaning it's a total length of periods. So the periods here in the online selling case is a number of customers. And we have the CT here, which is called cost observed in period T. Remember, this is a cost you can observe at the beginning of the period T. Before you make a decision which price to offer, you already know that cost. Okay, we assume that they are ID sample from a fixed but unknown distribution on the parameter set C here. And we assume that we have a number of price choices. We have k different prices we can choose from. And I want to draw your attention here to the profit function here. So the profit function here is a function of the cost C. So suppose if you pick up the price P sub k, so then your expected demand would be E of this D. So this D here is a random quantity that we don't know. So it's that given the price, so what sort of demand you are going to observe. We assume that it's not something we know. We also do not assume that it's a linear or whatever. It's long parametric. So then you have the expected demand and times the price minus C here. So just with a little bit algebra here, you can write this profit function to be pi k times 1 minus C divided by pk. Later I will show you why do we do that. And here so the pi k here is the expected revenue, but that's something we don't know. That's something we have to learn. What we know is that every time we set a price pk, we can have a random observation of this revenue. And we assume that it's bounded in a region we can normalize to the range of 0 to 1. Okay. So that's sort of the notation here. So So let's just look at a bit more. So we're going to formulate what a regret look like. So suppose that at a time t, at the period t, I observe this cost CT here. So then my actual best, I denote them as I star here. Because if I know the actual profit, so I can look at all k different prices and find the one which is highest. So that means if I know this mu, but of course I don't know. I have to learn, I have to have a pricing policy here. And suppose that my pricing policy is going to choose this I sub t here. So then the regret I have will be in that way. So I sum up over from T from 1 to this capital T here. So this is the optimum profit if I know everything. And this is a profit that I choose. So there's a difference here. The difference here is my regret. So I take the expectation. I want to draw your attention. So the expectation here is taken with respect to two things. First is a C, right? Because the cost here is changing over time. It's a random variable. And another thing is the expectations are also taken with respect to this IT here, because that policy depends on the previous information realizations. So there's two different layers of randomness here. And this is a regret. So what we want to do is we want to design some kind of sampling policy here, then try to minimize that regret. We want to do some analysis on what sort of a regret you might have. But before that, I want to just talk a little bit about why do we want to study this particular problem. Can I just say I'm not going to consider this varying cost, I just compute the average cost, and I put the average cost in, then I'm solving that as a typical multi-unbounded problem. Can I do that? Yes, of course I can do. So in that case, I'm really just looking at this particular problem where the C here should be, I said that as a expected cost. So then my policy will not change, always the same. But however, if you consider the cost change over time, the problem you're solving is this one. So if I look at the expected profit, I can compare the expected profit of this varying cost with that one. So by Jensen's inequality, because the maximum function itself is convex, so I know that by consider the varying cost, my expected profit is higher. My expected profit is higher. That's why we want to consider this problem. So I want to emphasize later on, when we do the regret analysis, our target is this one. So the target is actually higher than if you do not consider this varying cost. So we have a higher sort of a target here. We want to look at what regret do I have from that higher target. Yes, we'll assume that it's ID from a distribution. So there's a special feature here I want to emphasize is this what this profit function look like. So the profit function has this revenue part times this 1 minus C divided by PK. Remember at period T I observe C, I set price. So therefore this is known. You can think about this is known. So if you look at all this profit function here, they are straight function, they are linear function of C. Not only that, the linear function passing through P1, P2 to Pk, those has no randomness in it. So the only randomness that we don't know is indeed the revenue here, right? So therefore, even though I'm consider this a cost sort of profit maximization problem, but what I need to do from the learning angle, I only need to learn what the revenue function look like. So the revenue only appear here. The only appear here. So therefore, the precisely estimating this revenue is actually critical to our problem. So based on the intuition, based on this special structure here, we designed a pricing policy, very much similar to the upper confidence bound. So what do we do? It's very similar. I just want to say one thing. So what we do is, at any period T, I computed the upper confidence bound of the revenue for each revenue here. And I use that upper confidence bound of the revenue here to compute an upper confidence bound of the profit. So then what I'm doing here is that, so I'm going to pick up the arm or the price given the CT, which maximize this upper confidence bound. So I construct the upper confidence bound of the revenue, then using the upper confidence bound. So that's where revenue and the price is down there. So I'm going to construct this upper confidence bound of the profit. Then I can compare different profit at the different prices given the cost C. So I'm going to maximize that. So that's a policy we have. Very straightforward policy. And here are some main results. In the interest of time, I'm just going to skip the proofs. So we're able to show that if you have two arms, k equal to 2, you're able to show that the cumulative regret in this case is bounded by a constant times log t squared. So where does the regret come from? So the regret actually comes from the inaccurate estimation of the intersection point of mu1c, mu2c. So I have a figure here which is coming from our paper, which has all the proofs in it, but I'm going to skip that. But I want to show you that this is these two black lines are indeed our true profit function. And our estimated upper confidence bound are those two dotted lines here, so sort of the yellowish dotted line here. So the true intersection point is at O, while according to our upper confidence bound, our intersection point is at this O bar. You'll see that the regret will only occur if your cost is in that range, XO to XO bar. In this side, on that side, you're not going to have any regret. And not only that, so when you have a regret, you're going to have a regret here. The size of a regret is also quite small because they are quite close to this intersection point. Indeed, you will find that the order of this length here is actually the same order of this half width of the confidence interval. So both this is all of that order, this range is of that order, and also the sort of regret is also of that order. So the total regret for each time t is a multiplication of those two. So we are able to show that indeed for each t, the expected regret is bounded by constant times log t divided by t. So then you sum up from all the t from 1 to capital T by the integral rule, you can easily find that it's actually bounded by constant times log t squared. So we'll also be able to extend this result to the cases where k is greater than 2 under some conditions.
So in that case, 2 will be replaced by k? So if you have a general k, where would k?
So k will appear here.
Not in the power.
Not in the power. Not in the power. Will still be the log t square order. So it will be k times the log t square order term. But in the case of more than k greater than 2, we'll not be able to get this finite bound. We only have a sort of a big O in that order.
So in this case, is there no uniform O bar?
No, I couldn't find one because this area, so this multi-arm bandit with some side information has in recent 5 years been studied. But so far, because people only look at the general problems, the regret bound is usually polynomial. So mine is log t squared, so it's much smaller than a polynomial. Yeah.
But when k is larger than 2, I can see your picture easily gets complicated.
True.
The area would grow in what? In polynomial fashion of k? Or
No. Because the regret, let me pick up this. So the regret is still corresponding to, you think about each profit going to, so you only have the intersection point of 2 lines, right? So the regrets still only occur in that small neighborhood. So essentially, you have inherent order here.
If you have a K line, how many?
No. K line is supposed to have another line here. What matters is only that point.
Okay.
So you still just have sort of a K. So actually, K minus 1 intersection
The
points.
slopes are all-
Right. So sort of the intuitions here. So that's something I learned from Xiren. Xiren also said that he learned from Larry. Was that when you have a result, the proof is not enough. You have to give me an intuition, to have an intuition. So basically, what we learned, the basic intuition, the reason we could get a regret, which is not very high, is because the information learned from the one value of the cost can also be used at other values of cost. Because what we learn here is not a profit function. I try to learn revenue. And revenue has nothing to do with what cost you're going to use. So the information can be used. So therefore, I wouldn't consider this a very, very surprising result. But it does tell you that even though the problem seems a lot more difficult than the original problem, but the regret does not increase quite a lot. It's only considered to the original MAB, which is log t. Now, your would consider to be best now changing over time, while you still have a regret, which is log t squared. But I want to emphasize this point again. The regret comes from the inaccurate estimation of the intersection point. Because from here, it motivates us to think about a special scenario. Let's think about this. What if your cost here is a discrete? So instead of have a continuous cost, now suppose you have a set of a discrete point. If you have a set of discrete costs, so what happened here is, if just look at two arms, if I have two costs, so then there's a minimum gap for what this difference look like. So from an estimation point of view, so if my arms have, or if the revenues are estimated accurately enough, then it should overcome this minimum gap. It should overcome this minimum gap. If there's no minimum, if once I have a minimum gap, then that means if my sample size increase high enough, then the error of intersection point no longer matters. So what sort of regret will I get there? And we were able to show that in that case, if you have a finite set of costs, of course cost has to be greater than 1, and you have none of the feasible prices inferior, meaning that you always have a cost under this cost, this particular price is optimal. In that case, you will be able to show that your regret is actually bounded by a constant. So this is the case. I don't have to prove lower bound. I know it is a lower bound. I know it is a lower bound. So this, I claim, is a surprising result, because before we solve the problem, we expect the problem to be more difficult than the MAB. But in the end, you find that the regret is even lower. It's bounded by a constant here. And the reason for that is that because every price is now good for some cost. So in the end, so if you think about all the prices or all the arms, the number of pools you're going to have will increase linearly. So in the end, that means just when this optimum price occur, I pour that will give me enough learning. That means gradually, I only need to do the exploration. I do not need to do the exploration. So that explains that while in the end we can have a regret result like that. That was a bit surprising, but once we think through it, it becomes quite straightforward. So we're doing our extension now. We think about the cases if not in the dynamic pricing context. Let's say if I have linear arms, so all the arms are estimated through linear regression. So we're in the process of proving that in that case you can also obtain some results similar to this. So that's pretty much all I have. I have a numerical result here to show you that. So this is a case where cost is uniformly distributed between 0 and 4. So you'll see that it will increase gradually. I don't know by looking at this log t square or not, but it seems it's not as fast as linear. But if you look at the particular case where your cost takes only two values, 1 and 3, you will see that regress is indeed bounded by a constant. That's all I have. Questions? Okay.
So in the case of finite number of choices of costs, it would seem that the constant can be pinned down more, right? I mean, because in that case, probably the constant matters.
Right. Yeah. Constant matters. But when we do that, we only just sort of using the inequalities and trying to create a bound. We didn't really pin down, say, what sort of regret it will achieve.
Because you can probably prove a lower bound, a constant lower bound.
Constant lower bound.
Right?
Might be able to do that. Might be able to do that. Yeah, but the lower bound proof usually is quite difficult because Lander-Robbins actually using a sort of a change of a measure type of idea to do that. The proof was pretty difficult to read. Yeah. Yeah.